Refrigeration Technologies at refrigetech.com. Carrier and carrier.com. Don't miss the absolutely essential event in ACHR, the AHR Expo 2025, coming to Orlando, February 10th through 12th. Explore the latest product advancements, best practices, and industry trends, and I'll be there, of course. Register now for free at ahrexpo.com. NAVAC at navacglobal.com. The ESCO Institute, with over 200 HVACR training solutions, courses, webinars, and simulators. Find out more by going to escogroup.org. Hey everyone, it's Bryan with the HVAC School podcast. A lot of times when I do this, I'll do a funny little intro, or I'll do a meeting or something that I do with my technicians. But in this case, I'm not going to do that. I'm just going to sit here in front of the microphone and I'm going to talk through a couple things that I think are probably pretty common, either mistakes or things that new technicians or even experienced technicians who don't think a lot about this stuff are going to want to think about. And specifically today, I want to talk about what I coined as the 5 pillars, which I later found out was actually already a thing. I guess it's like the 5 pillars of Islam or whatever, but I called them the 5 pillars of the air conditioning, especially residential air conditioning diagnosis, a refrigerant circuit diagnosis, I should say. So when I initially first came into the trade, there was a lot of guys who, and someone on the group just made this comment, beer can cold is good enough when the suction line, and, just keep your suction above 75 on an R22 system, so on and so forth. Obviously those methods didn't work for me. I came out of school and I wanted to do things the right way. So I had to figure out some ways to know what's normal and what's not normal. And that's the issue in the trade, is that a lot of this stuff is like, all right, if your head is high, guys will say, well, if your liquid line pressure is high, well, but who's to say what's high and what's not high? We have manufacturer guidelines when it comes to charging, but when it comes to diagnosis, we need to have some guidelines for technicians to have some idea of what's normal and what's not normal. So when I talk through, and especially when I'm giving you something that's a rule of thumb, I want to be very clear that rules of thumb can be wickedly misused. The purpose of a rule of thumb is to give you some sort of basis on what is normal and what is not normal. And when I say normal, what you would normally run into on a properly running system. This is not to say that I'm saying that this is how you set in a critical charge. Obviously, when you're setting in a critical charge, you need to reference any manufacturer documentation for both components and the system itself. If you're installing a new system, a split system, for example, you should know the length of your line set, and you should take that into account when you're charging it initially, so on and so forth. So it starts with reading the documentation that comes with the equipment that you're installing or the piece of equipment that you're working on. But when you walk up on a unit and you are taking some readings that you're not sure if they're right or not, you want to have some kind of idea of what's normal, give you a baseline to work from. And again, this can be as easily misused as it can be used, but it's part of the journey of becoming a competent technician. You want to have all the tools in your tool bag. So these are some of those tools. So the first thing is taking suction pressure. And of course, to start with suction pressure is like, starting with sliced bread. It's like the most common reading that technicians take, and also the most common one that technicians abuse. For whatever reason, I get technicians who would tell me, I'm adding charge to the suction and it's not going up. I get that all the time. I'm adding charge to the suction and it's not going up. First of all, don't add charge to a system unless you know that it needs charge. Now, are there rare circumstances, very rare circumstances, when I will add a small amount of charge in order to see how the system responds to give me a little more diagnostic feedback? Yes, but it's very rare and only in certain circumstances. Okay, so to start with, suction pressure, what it really tells us is it tells us at what temperature the refrigerant is boiling in the evaporator coil. And even then, it only tells us that if we're reading it right at the evaporator coil. And as you know, most often we're reading in a split system, we're reading the suction pressure out at the condenser in the suction line. Well, things can change in between the condenser and the air handler. Now, thank goodness we have this thing called pressure-temperature relationships, which means that when pressure increases, temperature increases. When pressure decreases, temperature decreases. And that's true of something when it's in either liquid or vapor state, but it's even more so the case when we see something as far as the amount of heat that's absorbed when something is changing state. And so let me clarify what I mean by that. We move a lot more heat when something's changing state than when it's not changing state. Much more heat is moved. And when we use our pressure temperature correlations, we can tell when something is at its boiling state. We call that saturation. When you look at your suction gauge, because we're talking about suction pressure right now, when you look at your suction gauge and you see the temperature that needle's pointing at, or if you're referring to your PT chart, you can find the saturation temperature at that pressure. So that saturation temperature tells you if it's changing state, at what temperature it is changing state. Okay, and so we can look at that and we can say, all right, let's say if I'm on a system and I'm reading a 35 degree saturation temperature. That means that theoretically speaking, if I'm measuring near the evaporator coil, that it's 35 degrees inside that evaporator coil. Now, what if I'm not reading at the evaporator coil? Well, what we can do is we can take a temperature differential in between the outlet of the evaporator coil at the suction line there and then another temperature at the outside unit and then compare them. If we do not have a big change in temperature between those two, then we also know that we do not have a big change in pressure between those two. You get what I'm saying here? You get what I'm giving you? The only time that would not be true is if that temperature was at saturation, which would be called a zero superheat. So to recap, we're not getting into superheat yet. We're going to do that in a little bit. But to recap here, first thing that we learn from suction pressure is at what temperature the refrigerant is changing state in the evaporator coil, known as boiling or evaporating, or some people call it a flash gas, whatever you want to call it. It's changing state from liquid to vapor, and that's the temperature at which it's happening. Okay? So the first thing that you need to know is that if you have an evaporator temperature that's below 32 degrees, so you're reading at 32 degrees saturation or lower, that means that evaporator coil is going to freeze if at all exposed to water. Water freezes at 32. Now, what I'm not saying is that saturation temperatures under 32 degrees is always a problem. It isn't always a problem. Obviously, if you're working on a freezer, your saturation temperature has to be below 32 in that evaporator coil. But then you know that the coil will freeze. Another example of this is a heat pump system. In a heat pump system, the outside coil becomes the evaporator in heat mode, and the inside coil becomes the condenser. If you've worked on many heat pumps, you know this. Well, in order to transfer heat into that outdoor coil, in order to then reveal it inside when you're in heat mode, that outdoor coil has to get below freezing. The result of that, though, is that outdoor coil will build up frost. It will build up ice, and so you have to have some method of removing that ice, known as a defrost cycle. Okay? So it's not necessarily that it's always bad in every kind of system to be below 32 degrees saturation. That's ridiculous. But in a residential air conditioner that's functioning in cooling mode, where the inside coil is now is your evaporator in cooling mode, if you're working on a heat pump, you don't want your saturation to be below 32 because that coil will freeze. I've seen so many guys who get addicted to subcool or superheat, where they'll say, the system wasn't undercharged because I had a 10-degree subcool. And I'm like, yeah, dude, but you also had a 30-degree suction saturation temperature and you just left. He's like, well, my charge was fine. There's more things at play than just charge. These 5 things that I'm going to go through are not just about charge. They're about diagnosing the entire system. Okay? So when you have a low suction, there's many things that can cause you to have a low suction. You could have a restriction. In the expansion valve or in the liquid line, you could have a plugged filter dryer. You could have low airflow over the evaporator coil or multiple types of low load that could result in you having a low suction pressure. But you have to compare that with the other 4 readings. So this is one of the 5. So the other 4 in order to know what's going on. You have to think outside of the box of, well, is it overcharged or is it undercharged? There's a lot of systems that may have a perfectly fine charge, but there's something else wrong with them. Okay, and suction pressure helps you do that. So the first thing is your suction saturation below 32? Because if it is, the consequence is going to be freezing on a residential air conditioner in cool mode. Freezing inside is not okay. You with me here so far? Okay, great. Then from there, you can now know at what temperature your evaporator is boiling the refrigerant off inside the evaporator, and that can tell you, based on the load conditions of that evaporator, the area that evaporator is in, when you compare that evaporator to its ambient temperature, you can get some interesting information. So a good rule of thumb is a saturation temperature 30 to 35. And you guys, some of you experienced technicians out there are going to dispute this. I'm here to support the new guys. So new guys, you can support me here. You can back me up on this one. So a good rule of thumb, and I don't know where I learned this the first time. I don't know. Maybe I made it up. I don't know. But I think I might have learned it in AC School, which, heaven help us if we just apply everything that we learned in AC School, because a lot of it's bogus. But I think this one has served me well, is that your suction pressure, so that equates to a saturation, should be about 30 to 35 degrees below the temperature of the air, the ambient air that is flowing over the evaporator coil. So in the case of cool mode, that means that if your inside air temperature is 85 degrees, then your low side saturation, your suction saturation, should be 45 to 50 degrees. Now, is there a little bit of variation there? Of course there is. And does it make a difference if, what your fan speed is and so on and so forth? Of course it does. But for a new technician to walk up, and because what I don't want some technician to be checking a system in cool mode when it's 60 degrees inside and saying, oh, it's freezing, that's a problem. Well, no, in that case, it's freezing because the air temperature is just way too low. And again, I know there's other factors, the humidity content in the air or the moisture content in the air, the airflow. There's a lot of other things that can affect this, but that gives you an idea of whether or not your suction pressure is in the range that you think. So again, 30 to 35 degrees saturation below indoor ambient. So you take your indoor ambient, take 30 to 35 degrees off of that. That should be about what you would think that your suction saturation would be on a system running in cool mode with an air-cooled evaporator. All right, so that's that, and we're going to go in a little bit into the different failures and some things that can cause low or high suction pressures. But for now, we're going to go ahead and table suction pressure. So now we're going to move on to head pressure. Somebody asked the other day, why is it called head pressure? My guess is, and I could be wrong here, but it's that it comes out of the head of the compressor. So it's the side of the system. The head of the compressor acts as the separation between the low side and the high side. And so it's coming out of the head of the compressor. That's your head pressure. It's actually better to say what line you're reading, because coming out of the compressor is your discharge line. Your discharge line is radically different than your liquid line. So I actually prefer, when I can remember or when I can encourage my technicians to say it this way, I prefer them to either say liquid line pressure or discharge line pressure. So first of all, you don't have to ask, but then also it kind of helps clarify your thinking about what it is that you're reading. So high side pressure, head pressure, liquid line pressure is just as important as suction pressure when it comes to telling you how the system is doing. Okay. Now, I'm going to give you a rule of thumb on this as well before we go on too far. But the first thing I want to tell you is that your liquid line temperature, so the temperature of the refrigerant coming out of the condenser, has to be hotter than the temperature of whatever medium it's giving its heat up to. And so this is true whether it's water-cooled, air-cooled, whatever type of condenser it is. If the outdoor air temperature is, let's say it's 90 degrees, well, your liquid line temperature cannot be 88. If it is, then it's not a liquid line anymore. It's actually, I don't know what the word would be, but it can't be colder than the medium to which it gave up its heat in the first place. In order for heat to move, there has to be a temperature differential. So you have to have something that's colder than the refrigerant flowing through the condenser in order for it to transfer its heat out of the refrigerant into that outdoor air or water or whatever it is, okay? And so the liquid line temperature cannot be colder than the outdoor air, which means that it's going to be warmer than the outdoor air. And so that's something to think about when you're looking at your liquid line, because I've seen cases, and so this is actually bringing up a specific instance where I had a technician who was working on a Goodman system, and they took their liquid line and they said, oh, my liquid line, I have a really high subcool. And he gave me the liquid line temperature, and it was something like, 78 on like an 85 degree day. I'm like, well, hold up a second. You've got a restriction in your liquid line inside the condenser. And it ended up, like I said, it was a Goodman. And so it had, I think it was a Goodman or something. And it had a liquid line inside the condenser itself, a liquid line filter dryer inside the condenser itself that was restricting and causing that temperature to be like it was. And so you had a big temperature drop across that liquid line filter dryer. Duh, obviously, your liquid line cannot be colder than the medium to which it's giving its heat up to. Otherwise, the process would reverse and heat would actually come out of, in this case, the outdoor air and go into the liquid line then, which is that's not how it works, okay? So this goes into this whole range of things of, when technicians claim magic, and whenever they claim magic, it's either because something's wrong with their tools, they're doing something totally wrong, or they're just missing the obvious. So I'm going to give you a rule of thumb here. And again, this varies quite a bit depending on the type of system and so on and so forth. But a good rule of thumb for head pressure, in this case, discharge line pressure is going to be higher than liquid line pressure. So in general, this is more liquid line pressure. So discharge line, you would expect to be a little higher. But you would generally expect your liquid line pressure to be 15 to 20 degrees saturation above outdoor ambient. Okay, so if my outdoor air is 90 degrees, then I would expect it to be 105 to 110 saturation. And that's not liquid line temperature, because the liquid line temperature is going to be colder than saturation because it's subcooled. Subcooled means you go below saturation. We're going to cover that in a second. But I would expect the saturation to be 15 to 20 degrees, maybe a little more than that, but in that range, higher than my outdoor ambient on my liquid line pressure. Discharge line pressure is going to be a little higher than that. All right. And again, type of system makes a big difference. I keep saying this, but the reason why I keep repeating myself about the type of system being different is that you can't be closed-minded as a diagnostician. And if you take what I'm saying as any sort of gospel, like, oh, well, I heard it on here, give me a break. Things are changing all the time. Feel free to oppose my rules of thumb that I give you. But anyway, so that's head pressure. Liquid line pressure, discharge line pressure is a little different, but again, it's good to know what you're working on. Discharge line obviously is high pressure, high temperature vapor. Liquid line is obviously high temperature, slightly above ambient temperature liquid. All right, so next piece of my 5 pillars. My 5 pillars, they're mine. I invented all this stuff. It's me. It's all me. Just kidding. I obviously learned this from other people, and these are well-known things, and I'm just communicating them to you. Superheat. First of all, the question I often ask when new technicians ask me about superheat, and they act like it's some sort of really weird thing, I'll say, okay, the air in this room right now, is it superheated or subcooled? And they're like, I don't know, whatever. Well, it's superheated. Why is it superheated? Because it's air, because it's a vapor. You can tell it's a vapor. You can observe it as a vapor. Things that are a vapor are superheated. That means that they are heated above their boiling temperature, above saturation. Okay? Things that are a liquid, if you look in a pond, that water in the pond is subcooled. That means it has been cooled below saturation. So very, very simple. The difference in a refrigeration circuit is that we can't see inside the lines unless you have a liquid line sight glass, and then you can see inside the liquid line, which is, I always argue that the guys who put in liquid line sight glasses, unless you're doing it for moisture, just take a Subcool. Subcool tells you the same thing. I digress. Superheat indicates to you that something is a vapor. So if something is superheated, meaning its temperature is above saturation, that means that it's a vapor. And there's a lot of reasons why this matters. And I could do a whole episode on superheat. I'm not going to go into all of it. But of the reasons why it matters is, first of all, we want to make sure that we're not starving the evaporator. If you don't put in enough liquid refrigerant in the evaporator, you will boil off too soon, and you will have a high superheat. You'll have an inefficient system. Okay, so you want to run liquid refrigerant through that evaporator coil as far as you can, boiling refrigerant. I said liquid. I shouldn't have done that, but it's boiling liquid, so flash gas. Refrigerant that is in the process of boiling, you want to be feeding as much of that evaporator coil as you possibly can. All right? And then you want it to stop boiling before it gets to the end to ensure that you don't run any boiling refrigerant, any evaporating refrigerant down that suction line. Because if you get liquid refrigerant into the compressor, it can damage the compressor for a lot of reasons. But it can damage the compressor. They call it flooding or slugging, depending on how extreme it is. But it's very common for systems to be set up in such a way that they flood the compressor. That's a bad deal. That is zero superheat. That's when you read a saturation temperature on your suction gauge, where the temperature that you're reading on the line and the temperature that you're reading on your gauge read the same. That's zero superheat. Now, I've had so many technicians in my career who have referenced negative superheat. I had a guy who actually was a trainer. I was just out of school, and he said, oh yeah, this system has a -5 superheat. And I said, Jimmy, that's not possible. You can't have a -5 superheat. He said, no, it's got a -5 superheat. Look at the reading. Well, when you read a negative superheat on your suction line, that doesn't mean that you actually have a negative superheat. What it means is that either your pressure gauge or your thermometer aren't reading correctly, or both. And so you can't trust your tools like that. You have to regularly check your tools against other tools. Thermometers are easy to check because you can put them in melting ice. So you take the ice, put it in some water, stir it around so it's melting so you know it's 32 degrees, and then put your thermometer in there and check it. But you can also just check thermometers against each other. Gauges, you have to make sure you zero them out and then just check them against other gauges from time to time. So if you get two sets of gauges, which you should have if you're a technician, check one and then check the other and see if they're the same. If they're not the same, then figure out which one is the one that's off by checking it against another set. These are some common sense ways to check your tools. But when you see a negative superheat, that's indicative of something wrong with your tools, either your thermometer or your gauges. All right. So negative superheat isn't possible because negative superheat is subcool. All right. Zero superheat means that you have liquid coming down your suction line. If you have liquid coming down your suction line, that's a bad deal. So we want to make sure that we have some superheat. Depending on conditions, the type of metering device, you're going to see anything from a 5 all the way up to 24 degree superheat. If you have a piston system and you're charging by superheat, you need to be measuring your wet bulb temperatures. You need to be using some sort of a slide rule. There's some really good superheat charts that exist, but the easiest way is to get a little superheat slide rule for a piston or fixed orifice system. But the majority of systems that we find today are TXV systems. That's the majority. A TXV is a constant superheat valve. I'm not going to go into all of that right now because you can go back and listen to my podcast that I did on TXVs. We cover everything about TXVs. But the TXV's job is to maintain a TEV, TXV, constant superheat valve. They're all the same thing. Its job is to maintain the superheat at the outlet of the evaporator. So when you measure a superheat, again, at the outlet of the evaporator means that if you're measuring it outside, that's not adequate. You would also then have to check to see if you have any significant temperature increase between outside and inside to know, because TXV sets the superheat at the outlet of the evaporator where its bulb is attached, not out of the condenser where you are if you're on a split system. Regardless, the job of the TXV is to set a superheat. So when you're checking a superheat on a TXV system, you're generally going to see more like an 8 to 16 in that range is going to be more what you see. If you see a 2, first check your meter and everything, but that sounds too low. The TXV is likely remaining too far open. If you have a 0, then obviously it's too far open. And if you have a 24 or 25 or 30 degree superheat on a TXV system, then it's too far closed. So that tells you something about the TXV. When you're charging a fixed orifice system or checking a fixed orifice system with superheat, then you have to know about the load conditions. You have to know about the ambient air temperature. You have to know about the moisture content in the air in order to know how the evaporator is going to respond, because that orifice in a fixed orifice system, it takes in refrigerant and it spits it back out. It doesn't change at all. It doesn't fluctuate. So in order to set your superheat in such a way so that you don't flood the evaporator coil when load conditions drop, you have to set it high. So when load conditions are such that let's say you have a situation where you have very hot, high humid air inside the home and you're running a straight cool residential system in cool mode and it's a hot day, it's 95 degrees and high humidity inside, then you're likely going to need to set your superheat very high, 20, 24 degrees, something like that. So that way, when the load conditions drop, you're not running liquid refrigerant, boiling refrigerant down into your suction line, because you don't want any liquid refrigerant in your compressor or in your suction line at all, because that's a problem. Okay. So superheat tells us a lot about the load on the evaporator. It tells us a lot about how far that refrigerant is boiling as it goes through the evaporator. So a common example, and I'm going to get ahead of myself a little bit here quickly, but I can tell by walking up to a system, grabbing the suction line, whether or not, I shouldn't say, I'm going to overstate this, but I guess this is radio, so I'll overstate it on purpose. In most cases, I can walk up to a system, I can grab the suction line and I can tell you whether or not it's low on charge or not, or whether or not it has an airflow problem. If you have a freezing cold suction line, it's not usually low on charge unless something's already frozen. The evaporator is freezing back. But in most cases, you can go up and grab it and suction line's freezing cold, and then you have a low suction pressure. That's indicative, if you know that your evaporator coil is ice bound, that's indicative of low airflow, because you wouldn't have a 0 superheat and low suction pressure if you didn't have low airflow. Because if you because what that means is that the refrigerant isn't boiling. It's boiling throughout the evaporator coil so much that it's actually liquid refrigerant is still ending up in the suction line. If it was starving the evaporator coil, then your superheat would be high because it would be boiling sooner in the evaporator. It'd be boiling off, and then it would be all vapor, picking up heat as it goes through that evaporator before it comes out. So it's a little something to think about. I talked way too long about superheat there in a rambly way, so we're just going to go into subcool now. All right, so subcool tells us whether or not the liquid line is full of liquid. That's really what it tells us. So when you take a 0 subcool, that's telling you that there's still some vapor. It hasn't fully condensed in that liquid line. So 0 subcool is a no-no. If you're looking at a sight glass, that's basically what a sight glass does, is you can see the bubbles of vapor still in there, which is an indication that it's not fully a full line of liquid. Subcool is a super useful thing because it tells us that it's fully condensed and that it's actually dropped temperature in the liquid line. Another neat thing about subcool is as you're dropping heat off, once it's fully condensed, that actually improves the efficiency of your evaporator. So a system with a 5-degree subcool or 10-degree subcool, the 10-degree subcool system is going to be slightly more efficient because that evaporator doesn't have to drop off those other 5 degrees. So this has actually been, lab demonstrated. So obviously you set your subcool based on manufacturer specifications, but you don't want to have your subcool be too low because that leads to inefficiency in the system. But the point is that for a metering device to do its job, for a TXV to do its job, it has to have a flooded liquid line coming to it. It has to have a full line of liquid feeding it for it to do its job. If it doesn't have a full line of liquid, so if there's a 0 subcool, then the TXV can't do its job. It's going to starve the evaporator coil. It doesn't matter how wide open it goes. It doesn't have a full line of liquid to work with in the first place. So you have to get some subcool, which is temperature below saturation. Just like superheat, there's no such thing as a negative subcool. So if you're reading a negative subcool, check your tools. There is such thing as a 0 subcool. It's also good. I think part of the reason why manufacturers like to see subcools higher, in addition to the efficiencies, is that when you set them a little higher, it gives you a little wiggle room in case your gauges aren't perfect or your thermometer isn't perfect. Which, by the way, if you're new to the business, you need to have a good set of digital gauges, a set of Testos or S-Mans. I don't care what you like. Just pick something that you like and use temperature clamps on your line, good quality temperature clamps. I have an old Fluke temperature clamp that I've used, 16 years. And it's the same. Well, actually, I shouldn't say. I was going to say it's the same one. I don't think it's the same one. I think I got another one in like my third year. So it may be 13 years. But anyway, I've had that same temperature clamp forever, and it's worked great. So if you want to buy the cheap ones and replace them every couple months, that's fine. But get yourself a good set of gauges and a good set of temperature clamps so that way you can get your subcool and superheat and you don't have to jump all over with your thermometers. Anyway, that's an aside. But typical ranges for subcool are 5 to 14 degrees. Check your subcool even if you have a piston system or an fixed orifice system. Check it every time because it still tells you something. If it's a TXV system, that's when you're setting your charge. I'm doing air quotes here, setting your charge by subcool, and use manufacturer specifications. Another thing I want to mention real quick is always use manufacturer specifications. If you still have the little pamphlet, like the trains have the little pamphlet with the charging curves and all that, look into that stuff. That gives you great information. Use that in lieu of any rule of thumb that I'll ever give you. Listen to what the manufacturers have to say. With the exception of Lennox and approach method. What the heck is up with approach method? I hate approach method. I always did. I think it's a dumb way of doing it, but they can do what they please. But anyway, listen to the manufacturers, including Lennox. I'm not happy about approach method. I digress. Moving on. So 5 to 14 degrees is what you'll generally see as far as subcool goes, but follow manufacturer specifications. Evaporator air temperature split. This is kind of old school. To any of you out there who are checking if your system is working by just taking a split, stop it. You've got to check all 5. The split is, I don't want to say it's the least important of the others, but it's my least favorite because it can be so easily misconstrued. It's a weird thing because you can have a high split because of having low airflow. You can have a high split because the system is a high efficiency system and it's running a low blower speed. You can have a low split because a system has too high of airflow. You can have a low split because the system's hardly working. And there's so many reasons why you can have a high or low split that it's only useful when it's compared to the other readings. Now, the other thing I want to say is that an air temperature split, a dry bulb air temperature split, doesn't tell you the whole picture because air, just based on its sensible temperature, that doesn't give you the whole picture of the enthalpy of the air, the total heat content of the air. So if you really want to get down and dirty, and we're not doing this right now, but if you really want to get down and dirty into how a system is functioning, you actually have to know its wet bulb split. There's Fieldpiece makes and I don't remember the model of it right now, but they make a meter that you can actually read wet bulb temperature in and out of the return and supply. It's pretty cool stuff. I wish I had a lot of this stuff when I was coming up through I wish back in my day we had this fun stuff, but anyway. So that's what you would need in order to have the full picture, but it's okay. Use your pocket thermometers, take a split. The split does tell you some things, but really what it's telling you is the air conditioner is doing something. It's telling you that. So you know that. It gives you something you can tell the customer, like, hey, it's putting out 60-degree air, so that gives you that. But the whole idea of having a 20-degree split, that's kind of a misnomer. You're going to see 16 to 22 as a rule of thumb and normally, and when it's on the high range, then that's generally, wanting you to look at low airflow when you have a high split. What's your filter look like? What's your coil look like? Did someone jam a dirty filter in the return somewhere? If it's on the low end, then you want to look at system capacity and potentially maybe having too much airflow. But I mean, really, let's be real honest. Is too much airflow generally a problem in our trade? Not usually. Okay. So now we're going to go into the diagnosing with the 5 pillars. Now, I'm going to make, if you're a junior technician, I'm going to make your employer very happy if you actually listen to this. So before you call a manager, or before you call a senior tech, I want you to always have the 5 pillars. But in addition to that, I want you to know indoor air temperature. I want you to know outdoor air temperature. I want you to know what type of system it is. So whether it's heat pump, straight cool, furnace, the brand. It would also be nice to know if it's variable speed blower or if it's a multi-stage condenser. And we're talking residential here again, people. Okay, so don't hassle me too much. I know there's a lot more in the world than just that. And then I also want you to tell them right away what type of metering device there is, because whether you have an expansion valve or a fixed orifice, that makes a significant difference in how the system can function, especially on the superheat, subcool, suction pressure, even the split side and things. So if you give them all of those, suction pressure, head pressure, liquid line pressure is what generally you would give. So suction pressure, liquid line pressure, subcool, superheat, air temperature split, indoor and outdoor temperatures, what type of system it is in general, and then what type of metering device you have. Man, I mean, you're going to sound like a genius. If you want to get amp draws and all that stuff on top of it, great. I wouldn't get too much more crazy than that, but that's some really good information. Most good senior technicians can tell you a lot about a system just based on that. And then beyond that, they'll maybe ask you for some temperature differentials across different components on the lines and so on and so forth. But it gives you a really good start into the system. So I'm going to go through some common failures associated with low and high on these different things. And again, this is not a full list. This is only a partial list, but it gives you some things you can think about. Good technicians are always learning new causes of different things, but meaning that, you'll find out, oh, shoot, I never thought about what would happen if a condenser fan motor, someone put in the wrong size blade on it. Which, by the way, if they put in a not pitchy enough blade or too small of a blade, it'll result in high head pressure. But that's not going to be on this list. There's all sorts of different things, especially when it's caused by the installer or the homeowner doing something crazy. You'll run into some really weird things. But I just want to go through a quick list here. So low suction pressure can be charged by low on charge, but don't just assume that things are low on charge when they have low suction pressure. It can be caused by low indoor airflow. So things like, when I say indoor airflow, low evaporator airflow. Dirty filters, dirty evaporators, kinked returns, damaged returns being too small. I say kinked returns because in Florida we have flex duct everywhere, and most returns are made by flex and they kink like crazy, especially in mobile homes, which we won't get into that. Not enough supply ducts or improperly sized supply duct work, anything that's related to your ductwork not being large enough. Your blower wheel being dirty, your blower not running the correct speed. You see a lot where people don't set up multi-stage equipment properly. They take a single-stage unit and connect it to the Y1 terminal. That's something we used to see a lot on variable speed equipment. So the blower is only running a portion of the correct speed. It's not being set up for the correct tonnage on variable speed equipment. Insulation pulling up against the blower. They'll pull off the door sometimes and pull up against the blower. Another common cause of low airflow that you see a lot is A tenant jamming a filter inside a return that's not supposed to have a filter. It sucks up into the duct and you can't see it, but sometimes you can hear it, and you go and you look up there with a flashlight and you see this old nasty filter jammed in the return. You see that one. We see that one quite a bit in Florida, especially in tenant occupied spaces. So those are low airflow. Metering device restriction. So it's restricting flow too much. It's closing down too much. It can be because it's closing down too much, or because, the screen before it is plugged. So in some cases, you can actually resolve a expansion valve issue by removing the screen, putting in a line dryer in certain circumstances. Liquid line dryers, obviously the restrictions on liquid line dryers, you diagnose almost all restrictions by looking for temperature drop across the perceived restriction. Copper kinks can also cause restrictions. Low ambient temperature, so you have low indoor load, again, unit and cool mode. But any type of low load on the evaporator coil, meaning low temperature, low airflow, can cause low suction pressure. You could have a kinked suction line, very rare, but I've seen cases where suction lines are kinked almost in half in between the air handler and the condenser, where you're reading your suction pressure on a split system. Could have an internal evaporator restriction. High suction pressure, overcharge, but again, don't assume it's overcharge. It can be caused by high suction pressure, can be caused by high evaporator load, high indoor temperature, high humidity. Anything that causes there to be a lot of heat absorbed into the evaporator coil will cause the suction pressure to be higher. That's this pressure and temperature relationship thing again. Higher temperature, higher pressure. Lower temperature, lower pressure, and vice versa. All right. So these, again, we're talking high suction pressure here. A metering device allowing too much refrigerant flow. I've seen people put in orifices that are way too large, or have expansion valves that fail open. You can have a piston seating improperly. That's also common in heat pump systems. Pistons seat and unseat in a lot of applications, depending on the flow of refrigerant. So if that's not seating properly and it's allowed to bypass the orifice, that can cause it. High suction pressure can be caused by poor compressor capacity, poor compression ratio in the compressor. That's what I was trying to say. Poor compression ratio inside the compressor. And so that can cause your suction to be high. In that case, you're going to accompany that with, you're going to have high suction and then also low head pressure, low liquid line pressure. You can have, in a heat pump system, you can have a reversing valve bypassing internally, where it's allowing refrigerant to flow from discharge straight into suction. That can cause you to have a high suction pressure. Low head pressure. It can be low on charge. It can be low ambient temperature. Low, like low outdoor ambient. You have a system running in cool mode and it's really cold outside, your head pressure is going to be low. You can have a metering device allowing too much refrigerant flow. So if the refrigerant's not being properly restricted, anything that can cause you to have high suction can also cause you to have low head. Reversing valve bypassing, compressor not pumping. You can, there's a lot of other things that can cause that, but a wet condenser coil, that's another common one. Wet condenser coil can cause your head pressure to be low, and you see that with a lot of new technicians when they're doing their maintenance. They turn the system on like, whoa, man, my head pressure is really low. Why is that? And that's why. You got to let it dry. High head pressure, high liquid line or discharge pressure can be caused by overcharge. Can be caused commonly by low condenser airflow, or whatever medium is removing the heat off of the condenser. In pool heat pumps, we work on a lot, or in geothermal, if there's low water flow over the condenser, that will cause you to have very high head pressure in certain circumstances. If the metering device is restricting too much, closing down too much, that can cause you to have high head pressure. High ambient temperature, that can cause it. A liquid line restriction can cause high head pressure slightly, and it depends on the circumstances on this. This isn't usually like if you see really high head, it's usually not because of a liquid line restriction. Other types of restrictions can cause it. Non-condensables in the system. And again, non-condensables are gases that can't condense, like nitrogen or air or argon or carbon dioxide, things like that. If you have a heat pump system, then remember that when it's running in heat mode, the inside coil now becomes the condenser. So now dirty filters can cause high head pressure. Low airflow inside can cause high head pressure. Anything that would cause low suction pressure in cool mode now causes high head pressure in heat mode on a heat pump system. All right, now let's do low superheat. So low superheat can be caused by overcharge in the case of a fixed orifice system. It can be caused by low airflow. That's a really common one. Low evaporator load, low evaporator airflow. So that's dirty filter, dirty evaporator, kinked return, return too small. All the same things that cause low suction pressure can also cause low superheat. The metering device allowing too much refrigerant flow, so it's overfeeding the evaporator, that can cause it. That can be a fixed orifice that's too large, a TXV that's failing open, piston seating improperly again. Low return air temperature can cause it. Internal evaporator restriction can actually cause it. I've seen this happen where part of the evaporator coil isn't being utilized, so it's only feeding some feeder tubes and not others. One thing to do if you want to look for a restriction inside of an evaporator coil is allow it to freeze and then watch for freeze patterns. So like you would disconnect the blower and then allow that evaporator coil to freeze all over. And when you see certain areas that are frozen, which would indicate that refrigerant's flowing through them, and other areas that are warm, then that would indicate a restriction in the evaporator coil. Or if you have one of these fancy new FLIR thermal imaging cameras, you can tell just by shooting it with the thermal imaging. You can also so now we're going to go into high superheat. It can be low on charge, metering devices, TXVs sticking closed. That can happen. Obviously, we see that a lot. High return air temperature. You can have high superheat just because your load is really, really high inside on a fixed orifice system, and that's actually kind of by design. Liquid line restrictions can cause it. Filter dryers, clogged screens, kinked copper, compressors not pumping. So if you have a compressor that's not pumping, that's going to generally result in high superheat. Reversing valves bypassing can also cause high superheat. Low subcool can be low on charge. Metering device overfeeding, so that would be too large of pistons, TXVs too wide open. Dirty condenser coils, anything wrong with the condenser fan blade can result in low subcool, high condensing temperatures. High ambient surrounding the condenser, so really high load can cause low subcool in certain circumstances. Again, it's not really commonly what you'd see. And again, it depends on the type of system. High subcool would be due to overcharge, metering device restricting too much, so closing down too small of an orifice, a TXV closing shut, anything that causes the refrigerant to kind of sit in the condenser, the refrigerant to be pumped in the condenser, not allowed through the low side, will cause you to have high subcool. So that also causes wet condenser coils can also cause you to have high subcool. So if you had a little rain and then you check it, your subcool is going to be higher. Now, let's talk about airflow real quick. Actually, I already kind of did this, which, airflow, you have to take it into account with the rest of the system. So a common thing would be like if you have a low suction pressure and you also have a high evaporator temperature split, then that's an indication of low airflow. Because if it was low suction and then it was also a low split, then that would be more of an indication of a capacity issue. But by the time you throw superheat in there, you know which it is. And if you have low airflow, you're going to have low superheat, low suction, high normal to high split. If you have high airflow for whatever reason, then you're going to tend to have a higher superheat and higher suction pressure. So again, high airflow isn't very common. You usually know high airflow because of air noise and other things, poor dehumidification, that type of thing. You're usually not diagnosing a system because your pressures are telling you, or something in your diagnosis is telling you that your airflow is high. Generally speaking, you're chasing, why your airflow is low. But there's also other things, where a typical split can tell you, like if you have a system that has heat strips, if you have a really low split, well, then to look and make sure that your heat strips aren't running as well, which is kind of a good final fail-safe. So I'm not telling you not to take a split. It is important to take. It's just not as important as a freestanding reading. It's only good when you take it in conjunction with the rest of your readings. So this has gone really long. You can find out this entire list by going to hvacrschool.com and finding out more. Thanks for listening. Have a good one.